So if we consider this as your input, X, this would be your hidden layer, H1, right? This would be your layer X. This would be your hidden layer H. And we are trying to learn the weights here. So this is your encoder, this is your decoder, and this is what we are trying to learn. We are trying to learn the weights for this input X. This is your hidden layer H, for example H1, and we are trying to learn the weights here. And then when your network, this is your output, so it should be nearly the same as X dash. This is the best result, that the minimize the error between these two. So once it is minimized, our network is trained, and we can copy the weights. Which weights we are interested to copy? The trained weights. These weights. And one more representation that we have here. So if we have the weights W here, we will say that these weights are W dash, and your W symmetrically relates to your W dash to the decoder side. So W symmetrically relates to your W dash. And here what we are doing is, this is W1, this is W1 dash, and what we are doing is, we have these weights, and we are trying to minimize our error function, which is a function of W and W dash. Minimize. This is our Euclidean norm of W1 and W2. And the best encoder, as I mentioned earlier, would be when your predicted minus your actual is equal to 0. And what we do then is, we have this target is to minimize. For this X, we have H1. This is your X dash, X predicted. And here we do the transformation, nonlinear transformation with your function f. For example, sigmoid, ReLU, whatever function we are trying to do, which is a combination of your weights multiplied by your X to obtain your Z. And once when we are done with this part, we get these tensors, these Z, W and Z are your tensors. Once we get these tensors, which are represented as a matrix form, of scalar values, we have our z, which is a transformation of your w1, this, and x. And what we do is, now once it is trained, your error is minimized, we simply remove this part. We chop off this part and we retain the trained part, these weights. So if the input x is given over here, we will have output from your h1, that will be your z1. So the output of this is a latent space z1. So the input is transformed into your z, which is your latent representation, and your features are derived from the input. z1 are your features that are derived from x1. We have this, we call this z as latent output. So from the first x, it passes to the hidden layer h1, and we have the latent output z1. And the method is that we are going to train our network to reduce such that we are trying to obtain whatever we have given at x, we want to obtain at x predicted, and in doing so we are training these weights w1, and this is your linear transformation. Output is your linear transformation z1. So now the next part is, we have trained we have copied the weight from this first layer, and the next part is, again we have, now this will be your h1, and the next will be your h2. Your weights here will be your w2 and w2 dash. Same way, what we will do is train the network. Whatever is the input here, it should be the output here. So we have chopped out this part. We no longer have this part, we only have this part. And now using this part of the network, we are trying to learn the weights in the next part. This is how we can do it. We input your x sample by sample, one by one, and obtain your z1, x1, xi into zi's, and then your z1 is input into your h1 to obtain your z2 here. Okay, so now we will have in the next layer, again minimize your error function, where we know it will be z1 bar, Euclidean norm, and it will lead to your nonlinear transformation to obtain your z2, which is a scalar multiplication of your z1 transform. So the output will be your z2, input z1, which was derived from x1 to obtain your z2. And when you have your z2 that is derived from z1, you will chop off this part, because this layer is now trained. you now have your Z1, you now have your Z2, which are the latent outputs, and now your Z1 will be given as an input into your next layer until we have all the layers. We have reduced layers, number of neurons are reduced, again number of neurons are reduced, and for Z3 we know it will be transformation of your scale multiplication of Z2 okay. So these are your derived values from Z2, and what we are doing is we are reducing your features. So the final representation is in this format. Again, when these weights W3 are trained, Z2 dash should match, and the nonlinear transformation gives us Z3. This is how we are extracting the features and reducing the dimensions. Now if we present it in the form of blocks, we can represent it like this. So we have H1, then hidden H2, H3, H4, and then we have, or Y, maybe a classifier. And this is your input X. And we have weights that we have trained in this W1 is trained, then the output layer is chopped, then this is retained, then W2 is trained, and the other layer, the decoder layer is chopped off, then W3 is trained, decoder layer is chopped off, only encoder layer, trained weights are remained here. Then we have, okay, this example only has 3 layers, but for example we have 4 and 5, up to 4 weights. Okay, this will be your output. So we can see up to W1, 2 and 3 the weights have already been trained, and we call the output after this as a feature extractor. So what do we notice here? In training all of these layers, we are trying to train these weights, right? Train the weights and remove the decoder part. This is the decoder part. And the encoder and decoder is the same. Trying to reduce the error between X and X dash. This is the pre-training part. So this is unsupervised training. Where we are not giving the labels. We do not give the labels, we only give we're trying to make the encoder output and decoder to have the same values. So this is unsupervised training, and we have trained our weights W1, W2 and W3. And now if we just unroll the network in terms of your Z1, Z2 and Z3, we can see that H3 the input is Z2, which is the output from H2. Similarly, input from Z2, and which is the output from H2, then H2 is input from Z1, and the output is X is output from the H1, and then if we take H1, then the input is your X. So we are going from here. Now what we are left is to train this W4 matrix, these tensors, and give the classification layer here. So finally we will have your classifier at the last layer, where your W3, W1, W2 will already be trained, and now you will add this layer to classify your output. Start this W Start this W4 with some random initialization as we have done before. But the advantage is that we already have these W1, W2, W3 pre-trained with random initialization, and then train whole of the network. Means train the weights, update the weights. But we already have a good initialization. This is what we mean by a good initialization. So what we did was we gave X to obtain our latent space Z1, then Z1 is given to obtain our Z2, and so forth until we get your output Y. And these intermediate pre-training that we have, they are there to give you or extract the features from your network and give you a good initialization point for your weights. So if we have an original image given like this, the output in this experiment is with stacked autoencoder, and this is the output from your principal component analysis. So we obtained that the results of the stacked autoencoder are much better than your principal component analysis. Why? Because if there is a non-linear relationship in the features, in the feature space, auto-encoded latent or intermediate space can give you more accurate reconstruction. Whereas in the case of principal component analysis, if we compare it with this, only certain predictions are considered. We will study the PCA in future lectures. And what we do is we project onto the first principal component and any information perpendicular to it is lost. So if we have nonlinear relationships among your feature space, stacked autoencoders are your way forward. Whereas comparison to your principal component analysis, they may not be that efficient. So for document classification, you can use your unsupervised pre-training and then supervised learning to classify your documents. And we can see here, this is your input, and you can easily classify your documents. So when we are done and we have extracted the features, feature extraction is done, extracted the features by pre-training. Next is the supervised fine-tuning now. So you add your fully connected layer now at the end and train all the weights. Fully connected works as a classifier. So if you have trained this, pre-trained this network and add your classifier layer at the end, you can use it as an encoder classifier. And only the weights between your last layer, last latent space, has to be randomly initialized. All of these weights are initialized with a good starting point. So that is the target of your pre-trained, supervised, unsupervised autoencoders. Examples where you can use them are deep relief network, stacked autoencoder, stacked denoising autoencoder, and sparse autoencoders. So these are some of these techniques that it can be employed. Next, we are going to study another technique to improve or optimize the deep network performance or training. And if you have any questions or queries related to today's discussion, you can email me and I will be vigilant to answer your queries. Thank you.